Okay, so today we are going to cover two topics, clustering, and also the second hour we have Louis Luo will come to talk about optimization. Okay, they both are very, very important topics in machine learning. I would say optimization is one of the most important. It's not a particular algorithm, just a whole framework to help you to estimate or guess those combinations of parameters to allow your model to fit the data the best. So this is a piece of art, and Louis is an expert on these topics, so he will give us a talk the second hour, okay? So clustering, and this is the machine learning people's favorite topics because it's an unsupervised method. You just rely on the data and look at data whether you have different groups of the those data points. Go ahead. So I will quickly go through several categories of the clustering algorithms, like k-means DB scan, spectral clustering, and SC3 is a package developed for single cell data. And also I will mention the hierarchy algorithm. So as I said, it's unsupervised, it's very different from supervised learning. In supervised learning, you need to have a training data, you regress, and for example, you found the curve or line, and the classification, you need to find the separation. And but unsupervised learning, you don't need that. You just look at the data and rotate it, okay, and then try to group them. So it's automatically organizing your data and understand the hidden structure, because if you don't know there are two clusters in your data, you treat them as a whole uniform cloud of points, you may get a different answer compared to you treat them separately, okay? So it's processing steps for most of the downstream analysis. In single cell data, we need to do clustering after dimensionality reduction. Then you are ready to group cells into this artificial created. They may not be the real cell type in biology, but at least from the visualization of the data, and we believe there are different subclusters, then as this typical workflow, you then to work on individual clusters and to look at their cell type or states of the cells. It sounds very easy, but sometimes the technique you use becomes tricky. For example, this is real data we get from a sheep sample from neurons, astrocytes, and some unknown cells. The quality is not high, but we have some embedding in the t-SNE 2D like this. If I run k-means directly, I get something like this separation, and three different colors. Each color indicates one clusters identified automatically by the k-means algorithm. You can try different run, and each time they give you some three clusters. But we, as a human, we probably need some cluster separation like this. It makes sense to us. So depends on the algorithm you use. There are some options, and you probably get different results. So major approaches including partitioning, and you cut the data point into two half, and then keep doing that. Hierarchy, you build trees, okay? So people use this in the molecular evolution, for example. You build a species tree, and this kind of a clustering algorithm. And model-based, if you believe your data was generated from some statistical distribution. And you can see, okay, I want to fit this group of data using this parameter, and then you found a fitting, and then you try another. So they're the model-based. And the density-based will solve the problem like this. So if your k-means doesn't work, you use a density-based approach, you get the answer which more intuitively sound like this. The difference between this cloud is the density is low in this huge cluster, right? So if you have an algorithm that can sense the density of data points, that give you the better answer. We will talk about quickly, and because I compressed 2 hours lecture into 1 hour. Okay, so k-means and model-based, we use the Gaussian mixed model, and dbScan is a density-based algorithm, and another density-based, which more recently published in Science, and affinity propagation and graph theory-based, and this spectral clustering, this like graph-based. You build a network basically for the cells. So this is a mathematical description of a k-means algorithm. It looks really weird, but if you will now be more familiar with before you take the class, I hope. So these 2 bars means what? The distance, the norm, how long this. So this is a 1 point, xi. So it's one of the points, okay? So, and the mu c is the center of this cloud. So you compute the distance between your data points to the center of your cloud. And then you take a norm, that's the distance. And you put the distance all together. So you sum all the distance. Basically, you have a lot of points here. You found an artificial center. Say, I want to consider my center is here. Then I just compute all the distance from each of the points to the center and put them together. D1 plus D2 plus Dn. So this translates into this I1 to n. Then you have di. So basically, that's it. Okay. So the center is this mu c. Okay, so this is an algorithm. So you want to make this as small as possible. If you put your center as your hypothesized center here, then your distance altogether will be huge. The only way you can make this smallest is you put the center in the middle of the cloud. So the pairwise distance from the center to each the data points in total will be smallest. Okay, so this has become an optimization problem. So you move your center to, you choose randomly, for example, in the space, which center will be gave you the smallest value here. Okay, but this is not a very hard optimization problem, because we know if you compute the mean of the x and compute the mean of the y and put your center in the average of all the data points, that you will get the smallest value here easily. So we don't have to bother to do this optimization framework or machine to solve this simple problem, because you can just compute the mean of x, y, and put the center in the middle. The problem with this is we want to put multiple data points here. So if you assume you have two clusters, for example, although you don't know, but you assume you have two clusters. In this case, I want to put two central noise. Okay, one is, for example, I want to put here the pink, and then another I put in this here as a green. This becomes tricky. You have two balls to juggle in your hand, and that's in this case it's called K2. So you have a pre-assumption you have two centers in this cloud. But if you think, okay, I have 3, so you can have a K equals 3. So this is a predefined hyperparameter for K-means algorithm. Okay, you have to give the algorithm the number of K. You can try different. At the end, you want to have this, for example, this distance, all the points to this distance, for all the points belong to red, you get this distance. You also have to do the same for this number, for this central. Okay, you get a similar expression, and you want to make both of them as small as possible. At the end, by the way, when you do this, you will assign numbers. So you will assign the data point 1 belongs to this, data point 2 belongs to this, and you only put the distance that belong to the same group. You only compute that. You don't compute, say, this belongs to the green ones. So I'm not compute the distance from the red category to green one. You only compute the distance within the same group. So you have to give K, you have to give pre-assigned categories. So at the end, you hope the solution will be something like this. At the end, you have your center move to the assigned group of data point in the center. So that's your final goal. And you get the total distance between data points to the center and the total points to the green center. Once you put them together, becomes smallest. That's not hard. That's everything seems you can draw here, nothing abstract. But it's just computationally, how can you achieve this very quickly, right? So that's why in the program, when you have this 3D, 2D embedding, then there's a button say, okay, I want to use K-means to group my cell into 20 different categories. You just take 1 second, you get everything looks fine. And so that's the trick part. So you compute this so-called between within the category. So you assign these values to this and compute the within the group, or within the group distance, total distance, within group total distance. Depends on how many Ks you want to minimize the total. Okay, this formula on the top, you have a bigger K, so that's bigger K is this. If you have a 2K and you have 1 category and you have 2 categories, so that's 2K. So for each category, you compute the distance within the category data points. And then after finish, you put, depending on how many Ks you have, you put every K together. So this is one level of the within the group, and then you put the total. So you want to minimize this total. Not only consider just one cluster, but you have to consider multiple, depending on how many Ks you have. So that's our objective function. So again, you will use objective function in optimization problem again and again. So your objective is to either minimize or maximize, depends on your goal of this objective, okay? You want to minimize this function here. So this is the algorithm, how this iteration is going. So we put a k, decide a value, and then randomly put a k, okay? You put red and the green points randomly in this space at the beginning. Then you found, you assign membership by distance. If I have a point here, which close to green one compared to the distance to the red one, I assign this blue point into green category. So after that, I will compute the within group total distance for green one, and then separate for red one. So, but at the beginning, I'm just randomly put these two central noise points and let the algorithm to run from this initial step, then run next one. So, so next one is after I compute this, I will move this central node. Depends on my calculation. So this is step 4, to re-estimate the center. So after you run the first assignment, then you run the second. And then, so the step 4 is most important. You update the location of your random guess, okay, based on your assignment. Then you do that again and again. Gradually, these 2 points will move to their optimal solution, okay? So let's see this in action. In this example, I put, it's also k equals 2, so 1, 2, 2 central noise position, and randomly put there. And then I found the distance. If the point close to this red triangle, it belongs to red category, and then yellow becomes yellow. So after this assignment, I will compute the average. After compute average, I believe, okay, this should move to the center of the red cluster, and the yellow should move to here. So that's my update. The first step is done. So after update, I will reassign the membership, okay? So after I move to the center based on the membership of those data points, and then I will restart, assign members to based on the distance. Now these 2 points in step 2 are more closer to the red triangle, so their membership change, become red. And then I do that again, the distance, and then move this center based on the membership of the other points. So after several steps, this whole procedure will stop because I have no way to move my center anymore. Then I reach the solution of this. Easy? Okay? So we are done with the k-means. Okay, so Gaussian model organism. So here you believe your data belongs to, remember the generator, the random number generator. So if you look at this data, you can assume I have 2 Gaussian process, and there's 2D as well. One gave you the data of this group, and then another gave you that group. So you can use 2D Gaussian distribution to regenerate data. So basically, you simulate, detect the potential model underlying the generation of those data. And here again, so you assume the blue points was generated by, this is like a 1D. This Gaussian distribution, and the yellow one from that. So you can fit your model. And this time, this is definitely optimization problem. You have a fitting of this. Okay, you change the parameter, change the mean, and also variance of the standard deviation of this distribution, allow those data points to fit those distributions the best. Then you solve the problem. All these problems have a limitation. They worked very well with this so-called convex shape, okay? But not very well for if you have a distribution of your data points looks like this so-called non-convex shape data. Another problem is the density, okay, as I showed you. So that's a limitation. It works very well for, it works okay for this kind of situation, but not so good for this. Okay, k-means will give you one cluster red here. Let me make this clear. So give you one cluster here, one cluster here. Okay, so because it's based on the distance, so if your centroid is here and here, it's completely fine. But this structure, this shape, will make this k-means algorithm feel confused. Okay. Again, this shape k-means will give one cluster here, one cluster here. K-means won't work for this kind of situation. This one here. K-means will give 1, 2, 3 clusters. Okay. So for those more complex, non-convex shapes, we need some other solutions. So this is a density-based spatial clustering. It's a long name, DB-scan. This paper proposed 1996. Okay, so it's a relatively new algorithm. It's based on the steps. Basically, you move your central noise along with the data step by step instead of just do the global pairwise distance. And this gave you like this small circle, and you move this circle based on the definition of your how many points assumed to be in the cluster in order to build a new cluster. If you don't have enough data points, then you start to build another separate clusters. And also, you have to decide how big your circle is. So there are some predefined so-called hyperparameters to run those kind of program. So this is a limitation for the algorithm because you select a different this number of minimum points in the cluster, or select a different length of the radius, then you get different results. But it's one of the ways to solve this density problem within the data. Okay. We will try this algorithm in computer session. We have a DB-scan in MATLAB implemented. And there are videos, and so this density-based algorithm will work okay. So with this kind of a situation, and the k-means also works fine, a density-based also solve the problem like this. Okay, k-means that definitely will not work. So there are many video you can watch. So dbScan is sensitive to the setting of the parameter. So again, this is a limitation. You need to have a educated guess and how the length of this circle and the radius you want to use. Otherwise, you get slightly different results. Not slightly, but sometimes like quite different results. Then there's a relatively new paper comes in. So this is 2014, if you can see. It's a very new paper. But I don't know why this kind of paper get into the Science. It's a top journal in the. It's just solve a very simple problem. This is how to predefine these values. Okay, based on some pre-process of your cloud data. Okay, to find some so-called outliers to give you the number of clusters and to find those density peaks. But there's just some computer tricks and to solve the problem. So they defined these two parameters in order to find those density peaks. Okay, so-called density peaks. So with this guidance, and you have density peaks predefined, then you start to use dbScan and to search for the clusters. Okay, another huge category is to find a cluster within a graph. And we are not going to talk about this much today because the graph theory and network we will cover in the later lectures. Graph is a network, right? And this problem is you try to have a network, you build a network for your cells, for example, and then you try to find communities. Okay, sometimes we call it sub-modules in the network. As communities, you have a family members, and they are clustered together. They are highly connected. Well, the others, one cluster is here, okay, and they are they're connected with other members by this kind of bridge. Okay, you want to find those bridge points and then define the subclusters. There's a whole thread, plethora of these algorithms to do this. Some fast, some slower. There's many publications in this field. Spectrum clustering algorithm. It's also graph-based. Okay, it's not to detect the communities. It's using eigen decomposition to learn from the matrix of the network. Okay, the network, you can represent the network as a matrix, right? If you have a node 1 connected with node 2, so you make adjacency matrix, and 1 and 2 is connected to 1, and 1 and 3 is not connected, you put 0 here, so you have a 1-0 matrix to tell you the relationship, the connectivities between nodes. So we are going to use that network matrix to cluster those nodes, okay? And the spectrum clustering will be applicable for all these situations. You can get this right, this right, this right. Is that cool? Okay. As I said, both of those will not, k-means won't work. Okay. K-means is really fast. It's several iterations get results of those correctly, but not this situation. Okay, who haven't heard about adjacency matrix? No? Everybody? Oh, you haven't heard about adjacency matrix. Okay. So adjacency matrix is a matrix representation of network. So if you have a network, for example, like this, there are 6 members in these 6 nodes, and they're linked by the edges, okay? And those edges can be weighted. Otherwise, you can put 1 there, each node here. Okay, so just 1 here, 1 here. And then you build this squared matrix. So adjacent matrix will be squared. Depends on how many nodes you have. Here in our sample example, we have 6 nodes, so you have a 6 by 6 matrix here. Okay? You put 1 between 1, 2 if they are linked. For example, 1, 4 is not linked in your graph, so 1, 4 is 0. Okay? 1, 4 is 0, 4, 1 will be 0 as well. They are symmetric because we don't consider the direction. For example, 1, 5, you go this way, 5, 1, go this way. They are the same. So this is an undirected graph, so you have a symmetric adjacency matrix. Easy, right? Okay. If you want to have information about the direction, for example, 5 to 6, it goes this way, but not 6 to 5, then you can put 5 to 6 here, you have 1, but 6 to 5, where? No, this is 5 to 1. 5 to 6 is here, and 6 to 5, so you put 1 as 1, another as 0, so you can go from 5 to 6, but not 6 to 1 to 5. Basically, you make this square matrix asymmetric. Okay, let's see. And you put 0 between in this diagonal position, because otherwise you assume there's a self loop. Okay, if you have 1 and connect yourself, you can put 1 in the middle. All right. So then we just compute. So once we have this, the first question normally we will ask is, how many connectivities, how many partners you have direct connection? For instance, 1 have 3 connections, 1, 2, 3. Okay, so in this case we call the node 1 have a degree equals 3. So what's the degree of 6? Degree of the node 6 has a degree 2. Node 4 have a degree 3. So we compute a degree, basically how many direct connections you have in this graph. So how can we compute those degrees? It's very easy. You can just look at the column here, and then you count 1, 2, 3. So this is 3. Basically, you sum these columns from the adjacency matrix. And 6, the node 6 have count 1, 2. So, okay. So it's very easy to compute the degree if you are given adjacency matrix. You immediately know which node have the most connectivities with other nodes easily. So we will compute this, okay? 2, 3, 3, 2. Okay, we have a node for 1, 2, 6 is 3, 2, 3, 3, 2, 2, right? Easy. So we haven't done anything yet. Just you give me the network. I redefined it using matrix and adjacent matrix and count how many connectivity for each node, and I put these numbers in the diagonal position. I create this matrix. So this matrix is called the degree matrix. Okay, it's very easy, right? You have adjacent matrix, that's a network itself, and degree matrix, that's just two matrices. And this matrix in this form is also n by n squared matrix. So we haven't done anything yet. So another is very easy as well. So you use the degree matrix minus your adjacent matrix. Let's create a matrix called L, a Laplacian matrix. Okay, this Laplacian matrix doesn't contain any new information. Everything is from your network, from your adjacency matrix itself. Just some of the transformation or rearrangement of numbers in there. However, this is very useful. This represents the whole network and also make you the next step computation convenient. There are a lot of structure within the network can be learned from this. Look at this Laplacian matrix. Okay. So the spectrum of graph theory is based on Laplacian matrix. It's one of the most important matrices, represent all the information in your network. The next step is we are going to do a decomposition of the Laplacian matrix. Now you should know it's very easy to do this step, the first processing step. You have network, you have that's a graph, then you build adjacency matrix, then build a degree matrix. The difference between degree matrix and adjacency matrix, and that's Laplacian matrix, the big L. And the big L, then you do this eigen decomposition, okay? So this matrix is a symmetric, and if you look at L, you do the flip and transpose it, and it's the same as before. Now in this case, we will have decompose, give you results of eigenvalues and eigenvectors. Okay. In PCA, we also did this eigen decomposition, but that eigen decomposition, remember, is worked on covariance matrix. It's big C, but here we decompose big L. And in PCA, we want to find the largest eigenvalue and its corresponding eigenvector. That eigenvector gives you the direction of your projection and then allow data points to be mostly separated. But here we want to have the second smallest eigenvalue and its corresponding vector. So if you reorder your eigenvectors, this is the largest one, and then you found this second smallest and its corresponding eigenvector gave you an indication of how you separate your nodes in your graph. And based on this, you can separate your node into, for example, based on the values here. Okay, those are the positive values, and those are negative values. So you know the separation should be in the middle, and the 1, 2, 3 is one cluster, and the 6, 4, 5 is another cluster. So it's this eigenvector gave you the information for your next step to group nodes in the graph into different clusters. So this is a spectrum clustering algorithm. Another example, this case, it's weighted. So look at those connections. They're not one. So your adjacency matrix will be not binary, 0, 1, but give you the weight. So the connection between x1 and x2 is stronger. x1 and x2, for example, the weight is 0.8. That means the connectivity, the strength is stronger compared to node 1 versus node 5. Okay, this is only 0.1. So what I want to show you is this clustering, spectrum clustering also works with weighted network. The difference is this is weighted adjacency matrix and degree. You compute it in the same way. You sum the total, but now it's not just connected members, it's a total sum of this connectivity strengths between this node with its direct connected neighbors. But also you run the same algorithm and compute the Laplacian matrix L, and then to the decomposition and find the second smallest, okay? And then do the separation. Same thing, same procedure. Basically, you use the smallest, second smallest to partition your data. Okay, this is an example. We will try. You load this small example prepared, and then use k-means to separate them into 3 clusters and plot out. Use scatter plot. It's a grouped scatter plot, and that's the results you get from k-means. And then you can run spectrum clustering. Okay, you get this. And spectrum clustering also works in many different situations. So that's comparison. So in the middle here is the result of the clustering algorithm, spectrum clustering compared to others. So DB scan is give you a result like this. Okay, comparable. Okay, there are studies to show different algorithm k-means and the DB scan in single cell world and compare the results. There are some comparisons, okay, studies. And we also, there's a strategy to use so-called ensemble clustering. So you try different parameter combinations, try different algorithms that take this consensus. Okay, if you try, for example, 20 different algorithms, change the parameters, change the case, and at the end, for example, these 2 cells always shared in the same members, no matter what your algorithm you use. So you have strong confidence that these two cells should be the same clusters, okay? Or 3 or 5 of them all the same cluster all the time. That's okay. Now if you have some cell, one cell here, and in 20 algorithm, 19 gave you the same cluster as a same member clusters. They'll probably still be the same cluster. So we use some of these combinations to try, but this just take longer, right? You don't want to stay there for long to get your results. And also, how can you take the consensus? How can you combine those results? Is also a topic people should consider. Do you want to give k-means more weight when they when the k-means say, oh, say these two cells belongs to same member of the group, or you trust spectrum clustering? So which one you believe would be better? Or you trust the hyperparameter setting in 1,5 against 2,3, or which one you will trust most? So there are many problems. Okay, SC3 is published in about 5 years ago, I believe. At end is using a consensus approach. So you build the clustering many times and then take this consensus to give you the final results. Well, they use k-means. They run quite a lot of k-means. At the end, combine those k-means to take a consensus. So that's the strategy. But before they run k-means, they did transformation, extraction of this information in different ways, and also slide the data by different degree of the dimensions before they run k-means. Okay, but how they prepare the data? First, you have input this matrix gene by cell. Okay, this is our big X matrix, right? And then the low quality genes or no less informative genes of this throughout to give you the truncated or filter, and then start to do this distance matrix. That's between cells. So you use all the informative genes and start to compare each cell against another using distance. They use 3 kinds of distance: Euclidean distance, Spearman, and Pearson correlation distance. Correlation, just you do the correlation between 2 variables. If you have 0.9 corresponding this correlation coefficient, you know, okay, these 2 cells should be very similar to each other, so distance will be 1 minus 0.9, 0.1. Okay, not too hard. But at the end you have a 3 n by n matrices. It's fine, right? Everybody knows this. And then they start to do 2 transformations for each of these distance matrix. So I use Euclidean distance matrix and did PCA, did Laplacian transformation. So each of these matrices becomes 2 transformed distance matrices. So now I have 6 matrices. Then for each matrices, they start to slide the data, and from using, for example, the top 5 components, top 10, top 15, until maybe top 50. So they did this incremental dimensionality range to do this sliding. And each time So now you have 6. So you repeat this for all the 6 matrices. And each time they did a k-means or treat this as an input variable, as inputs. So our input was here, right? Was here. Even after the filter, you have only one input matrix. So you can run this using k-means to give you one solution. But what they did is just distance matrix and transformation and using different dimensionality of the matrices and run many k-means and then put the results together. Okay? Turns out it works very well. All right? And we use this in single cell clustering and directly from basically directly from X. Okay? Without embedding. No t-SNE. The k-means we use from t-SNE, and it's like a 3D data. We do the clustering, but here we use this big X directly. It's just slow, and it works very well. And also for this spatial transcriptome, we have those spots, and in the spatial transcriptome, we also use SC3. Okay. So the SC3 you can find in toolbox here, and also in R. Okay, at the end, I'm going to mention the hierarchy algorithm, which based on the tree building and the partitioning, you just separate. So it's like 2 different strategies. And we build a tree all the time to understand the relationship between species. For example, if you have a data to support the shared common ancestors between species, you can rebuild the relationship between those. In statistics, we do have this dendrogram. Okay, so to do this dendrogram, you can set cut. Say, for example, you want to cut at a branch here, then you separate those nodes into 2 clusters. If you want to have 3, and you can cut from here, and you have 1, 2, 3 clusters. It depends on where you set the cutoff. The only problem is this procedure is slow. If you have hundreds of thousands of cells, 10,000 cells, so you build a tree. To describe this tree itself is already overwhelmed because you have so many internodes and connected nodes. Sometimes people use this to find outliers if you have one of this branch out here. I don't see many publications using this, but this is one of the papers. They use a dendrogram to separate the cells. And after they process the input matrix, and then do the distance matrix, and you can build this tree in order to do the clustering. Okay. There's another PCA. Okay. Questions? Yeah.
So in single cell data, clustering, what clustering means? Clustering means different gene belongs to
Different cells. Yeah, you can do the clustering for genes. It's okay. You can give it.
Means different cells belong to the same group.
Yeah, looks like the same group. Yeah.
Okay, so that instead of this function, how can you decide what is
Yeah. So Yeah, they have if you you put the cells into same clusters, they probably have a similar gene expression profiles, and they probably have a similar function. They belong to same type.
So after clustering, you see different color, right?
Yeah.
Different color.
Yeah.
That each point is.
Each color is a potential.
Color is not one cell. It's a.
Each color is a group of cells. Yeah.
Group of different cells or just one cell.
Different cells. So green cluster has such many cells belongs to that cluster.
So when you label, that means you label class.
Yeah, you label at this stage. You label the clusters. So you have cluster 1, 2, 3, 5, 4. Or you can label 1, 2, 3, 4. Doesn't matter. It just tell you the indicator.
Yeah,
Give you.
label is cell, right?
The label is cell group. The group of cells. Yeah. Okay. Any other questions? Yeah.
How do you do the annotation part? Like to find actually which gene belongs to this. So very bad part, like how do you calculate like this is the particular cell, like the annotation given? Or you make a marker, there's a marker.
What called? You mean which gene?
There's a marker, make a marker. Are you asking how to identify the cell type for each cluster? No, I'm like asking like how does the gene annotation get labeled?
Yeah, gene annotation. We haven't reached that step yet. So we just look at the relationship between cells and put them into groups. What do you talk about probably for the next step? So you want to know, okay, which gene responds for that particular group membership the most. So maybe because of the 3 genes highly expressed in those cells, that's why clustering algorithm move them into 2 same clusters. So we want to know what those 3 genes are. Yeah, that will be next step. Yeah, so you did this clustering and unsupervised. You didn't know which gene to look at them to put them here, but afterwards, you work backwards. See these blue clusters. Okay, which gene I express most, and other clusters don't express those genes. And you want to identify those genes. Yes, that's the next step. Yeah.
I have a question about the weighted
Graph.
activity.
Yeah.
So is that based on the log ratio, like how big the gene change?
You can have different ways to define the weight between nodes in the graph. Well, it depends on your question. So if you have a social network, is how many calls between these 2 members in the community, and you can give a quantity. Say, okay, they are connected, but they are strongly connected compared to they are connected, but they're once a month connection. So, yeah, in the cell network, yeah, you can have different ways to define those connections. Okay, yeah. All right, we can take a 5 minutes break, and Louis will come here to talk about the optimization. Yeah.
Can you change the yeah,
20?
yes, 20.
Is that right?
Yes, right.
Uh-huh.
Yeah.
Yeah, okay. Good morning, everybody. I'm gonna, as Dr. James say, I'm gonna present some optimizations concepts and some examples using some algorithms and especially of evolutionary computations. So this is the agenda, and okay, about classifications. Okay, maybe I have the concepts in the others, but in classification in optimization problem we have many classifications and a bunch of algorithms for every classifications. We have continuous optimization, discrete and inter optimization, and this is a list of algorithms we can use for these problems. Actually, I add a website. You can see every algorithms in details. Uh, Actually, there are some semester classes totally only for optimization problems. So I'm gonna show the most, I guess, the highlights. So optimization under uncertainty, complementary constraints, systems of equation we can optimize, and some system of inequalities, and multi-objective optimization. This is an area that some researchers are moving forward. Okay. An optimization problem seeks to find the largest or the smallest value of a quantity, such a maximum or minimum, given some limitation for the problem called constraints. And this optimization problem can usually be expressed as find the maximum or minimum, it depends about the approach, values for of some quantity q under a certain set of given conditions. So we have an objective function and we want to satisfy all the conditions. So this is a schematic view of the optimization process. We have a real world problem. We have some assumptions, abstraction of the problem data, and some simplification to mathematical models. And we implement with the math model, we have the optimization algorithms, and this implementation goes to the solution to the model, and we interpret this solution, and we implement to the solution for the real world problem, and there is a reflection, so we can complicate. We can go into more detailed situation, right? So we can have a new real world problem, and this is a no ending process. Okay. The general forms of optimization model is we have objective functions, and we try to minimize or maximize, right? And is subject to some constraints. In this case, for example, is greater or equal than 0, and these constraints are contained in a set. So this set is called the decision variables. So the goal is to find this vector that satisfies the constraint and achieve a minimum or maximum objective function value. So types of optimization model, stochastic, when the probability is changing along the time, deterministic. This is we can see a discrete, integer, continuous, linear, nonlinear. So we have a mix or different approaches that takes the best from every model. One example, imagine, that the very well famous traveling salesman problem. We have some cities, n cities, and we need to find what is the best route in order to optimize the time or the cost to visit all routes, right? So start from city one. What is the city one? Might be any of the city, and we need to visit each of the cities exactly once and returns to city one. So what is the best in that case? We have a proposal solution. So, but maybe the way is different, right? For each pair of cities, I and G, there is a cost traveling from city 1 to city J. So in this case, there is only one constraint, the cost. But we can add time, or we can add an order to visit cities. For example, Seattle should be the first one, or Portland is the last one, or we need to go to Seattle first, Portland, and I don't know what will be the city. This one, we can have a specific order to visit, and we can add to the constraints. Okay, the goal is find a minimum cost tour, and we can modulate this tour as a graph, as we have seen. This is so the problem now becomes to the shortest path problem. And in graph theory, we can find many problems and many optimizations algorithms. In a network, we have distance on arcs, source node S, and sink node T. The goal here is find a shortest path from the source to the sink. So in this case, this is a directed graph, because we can see, for example, we move from S to A in this direction, but we cannot from B to S. So this is a directed graph, and the algorithms should follow, or should follow or respect all these constraints. And these constraints are added to the set of constraints using some vectors. So here we can see some problems that can be modeled as a discrete optimization techniques, a scheduling problem. What is the best way to set flights or production lines in some factories, network design problems, facility locations, inventory management, transportation problems. So there are many applications in the real world that use this kind of algorithms. Minimum spanning tree problem, shortest path, maximum flow, mean cost flow, assignment problems. So for sure, every day we can see, especially if we are in the industry or academia, we can see some implementations using this kind of algorithms. So here we can see some solution methods for these kind of discrete problems: integer programming, network algorithms, dynamic programming, approximation algorithms. Specific with this last approximation is try to get or to go to the optimal solutions. The optimal solution is the best solution. So these kind of algorithms try to approximate instead of guarantee the best solution, because the problem is high dimensional and there are many constraints to satisfy, and these kind of algorithms are dealing with this kind of situation. Okay, in optimization we have this global and local optimization. In one minimization problem, we can find a local minimum. So imagine we are traveling from this point to this one. So imagine we have a simulated annealing, for example, algorithm, or a very simple. We want to see the minimum point. So here we can move forward. We can walk, and this point is the minimum, because the algorithms think, okay, I'm gonna go, and if when I start to go up, so we know that there is a minimum point. So these points are called a local minimum, but the algorithms try to find the global minimum. Here is very simple because we can see the global minimum, but in a high dimensional situation, we are not able to see what is the global minimum value. So algorithms try to find this point. Okay, so in global optimization, finding or verifying global minimum is difficult in general, right? Because we cannot see, or the algorithms is dealing with many constraints, is very difficult to find that value. Most optimization methods are designed to find a local minimum, which may or may not be global minimum, right? This is important. A local minimum may or not be the global. If the global minimum is desired, one can try several widely separated starting points and see if all produce same result. So go to this path. So we can start we can start at one point with some probabilities. So randomly, we can assign some points, and we can try the base logic. Okay, I'm gonna walk, and when I start to up, this is the local minimum. So we compare every point in order to see what is the global minimum. But we cannot guarantee, for example, we are going to start the points or start the path in all the path, right? Or so we don't know if our starting point is a good way. So that's why it's difficult to say. One algorithm is returning the global optimization. So in optimization, we can have some classifications, and not only discrete optimization or continuous, but convex and non-convex. In specific with convex optimization, many of the real-world problems can be formulated as convex optimization problems. So what is convex optimization? It's a branch of mathematical optimization, deals with minimization of convex functions. So a function is convex if its domain is a convex set and his graph lies above any of its tangents. So I'm gonna show you some examples to know what specific is a convex optimization. So a function is convex if the second derivative interval is positive on that interval. So we can see, for example, x squared. So the derivative, the second derivative is 2, right? So 2 is greater than 0. So that is a convex function. So, but not only considering that the second derivative is enough or sufficient, but we need to consider some other points. So a function, we can see the definition number 2. A function is convex is a line drawn between any 2 points on the function remains on or about the function in one specific interval between that 2 points. For example, we have this function, and we can use this point and this other point. So if we draw a line and all this line is above the function, so we know it's a convex function. So we have this question. In this linear function convex, the question is a linear function convex in this function? What do you think? no? In this function, what happens if we drop a line between any 2 points of this function? Is above of the function or on? Yes. So in this case, a linear function is convex. So the answer is yes. It's a line. We can select any of 2 points, and we can see it's a function convex. So we have also convex set. A set C is convex. Convex is a line segment between any 2 points in C lies in C. So we can see here, for example, in any 2 points of this set, if we draw a line, so it remains inside the set. Different with the second, with the right convex set. So the set on the left is convex and the set on the right is not. So we can see many figures. So we can see, for example, no convex. Why this is not convex, or convex this one, right? Yeah, this is a way to easily know that this is a convex set or not. So in global minimum, the most common problem is in convex optimization is to find the global minimum of a convex function. So it's something easy to see, right? So we start in 1 point and we are looking for the local minimum, but we can have this is a global minimum. Okay, so this is called the search space. Yes. So specific with global versus local optimal, we have this example, x squared. So the solution is 0. So this solution is a local minimum. This is also the global optimal. Okay. So we have a different function, x power of 3. This function. So the solution is 3 squared minus 34x plus 80 is equal to 0. So if we have, if we've solved this function using 2 points, 3, 33, and 8, we can use these points. So which is the best solution? Is the best solution the global solution? So we can see, for example, if for x 333, so we can see this value. So x is equal 8 here. So is the best solution the global solution? In here, for example, we don't know actually what is the best solution. So the best solution is 8, right, in this part. So is the global solution? No, because it's unbound. Actually, the best is 1, or one number between 0 and 1, right? So, but we can see it's a good solution, but it's not the best solution. Okay, so I will show you one example about these 3 different optimization programs or algorithms or techniques. Linear program, gradient descent, and some evolutionary computation. Maybe you have heard about genetic algorithms. It's very popular and not so popular as swarm intelligence. So the linear programming is a mathematical optimization technique. It's using to find the optimal solution, representing the constraints and one objective function, using linear a system of linear equation and inequalities. So let's see one example. Suppose a farmer has 120 acres of land on which to grow 2 crops, wheat and corn, right? Wheat requires 2 acres per ton, and corn requires 1 acre per ton. So the farmer wants to maximize the profit, which is 100 per ton of wheat and 150 per ton of corn. So we have another constraint, also has a limit of 50 tons of wheat and 4 tons of corn that can be produced, right? So we have a set of constraints and we have a objective function, is trying to maximize the profit. So the profit to maximize the linear equation is, well, this is not a question, this is a function. No, this is an equation, 100 W and 150 Z, right? Where W is less than and equal than 50, C than 40, and another constraint, 2W plus C less than and equal less and equal than 120. Okay, this is are the constraint taken from the exercise. So we can see this system of equation or linear equation graph in this part. So we have one function for every constraint, and we have this area. So our search space is this area. So we are going to use a simplex algorithm. This is one of the most basic way to understand or to use linear programming. So at step 1, convert the constraint of the linear programming problem into a system of linear equation, the standard form. So we have our original equations, and we convert to a standard form, right? So maximize Z and minus 100W minus 150Z is equal to 0. And subject to W plus S1 equal 50, C plus S2 equal 40, to W plus C plus S3, we add these constraint or these values or variables equal 120, and we have this another constraint, W, C, S1, S2, S3 greater or equal than 0. Okay? So we can have a table or a representation for every element of our linear system equation. We have a value indicating if we are considering or whether considering or not, right? For example, in the first equation, W plus S1 equals 50. So W, yes. C, not. S1, yes. S2, not. S3, not. Z, not. So the value is equal to 50. Okay? This is a simple way to represent. So at the end, we have W is minus 100, C minus 150. We are considering Z and equal to 0. Okay? We are just adding to a table. And actually, this is as we map the variables. So we can the step 2. We can use this. We can go through the step 2. Find a basic feasible solution, a basic, right, by setting some of the variables to 0 and solving for the remaining variables. Okay, so we have a non-basic and basic variables. So we have the starting point. Okay, and we are trying to move to the search space in order to try to find a local minimum, or in that case local maximum, and especially a global maximum. Okay, so we have tons of wheat and tons of corn. Okay, so the step 3, test the basic feasible solution to see it is optimal. So we got a basic solution and we are going to see it is optimal. it is optimal, the algorithm finish. So in the real world, is not common that our basic solution in the very beginning is the optimal. Does not happen. But actually, there are some researchers trying to find a way how we start the algorithm to run and close to the optimal solution. But this is a very is hard to set the algorithm in that case. It is not optimal. The algorithm selects a variable to enter the basis and updates the basic feasible solution accordingly. So here we have a negative values. So what we do, we multiply using Gaussian elimination to let the variable C enter the basis, subtracting row 2 from row 3 and added 150 times row 2 to row 4. So we run that operations, and we have this. So here we are moving to the new corner, right? Remember, we don't know this search space. I mean, we know, but we can see, but the algorithm doesn't know. So we have the new values, and we can see here because we did operation, and so we have a new value for the variables. And at the end, sorry, we had 6,000 for that equation. So we repeat the steps until the optimal solution is found. So yeah, at the end, so we got the optimal solution. Maybe there is a better solution, right? But we don't know. But the algorithm satisfied the constraint and got the ultimate solution for that iterations. So we can see, here we can see that trying to maximize 100 W plus 150 Z, and we got this solution. In that case, is 10,000. This is the value, the objective function actually for that value. So remember the problem or the statement is want to maximize the profit. So if they we have this value for every element. So at the end, using 10, 40, we're gonna have a profit of 10,000. Okay. So one other technique is gradient descent. Is one of the most common machine learning algorithms using in neural networks. Many of the neural networks is using gradient descent. This is a very well-known algorithm using only neural networks, but in data science in general, many techniques use these optimization algorithms and many of the machine learning tasks. So this algorithm and its variants can be found in almost every machine learning model. By the way, my research is trying to create a new version of this kind of algorithm using evolutionary computation, but I'm going to show you about these algorithms. So its goal is to apply optimization to find the least or minimal error value. So these algorithms considers the error value. Is mostly used to update the parameters of the model. In that case, parameters refer to coefficients in regression and weights in a neural network. So we can see in this graph the cost and weight. So the algorithms try to looking for or to search or to find the minimum cost. So use a vector called gradient. This vector describes the slope of the tangent tangent of the function graph. So M goes or points the direction of the most significant rate. So when the algorithms find a different rate, or the rate is not so significant, so that is the value the algorithms consider. Actually, for this specific problem, I'm going to show you by Thursday one implementation, and so we're going to be able to see a very graphical situation. It is a derivative that shows the incline or the slope of a cost function. Okay, so in gradient descent, we consider cost function minimizations of this cost function, minimum and maximum. There is a convex function, gradients, stopping conditions, and learning rate. So we see here a function, and we try to well, the algorithms, right, try to go to the minimal considering this slope. So specific with evolutionary computation, this is a part of computational intelligence, and computational intelligence is called weak AI. So AI considers robotics, manufacturing, is more open, but computational intelligence is more soft. So these algorithms are called as well meteoristics because use some heuristics to find some solutions. So some basic concepts about computational intelligence: the IEEE, Computational Intelligence Society, divides CI into three broad subjects: neural networks, fuzzy systems, and evolutionary computation. Inside evolutionary computation, we have evolutionary algorithms and swarm of intelligence. Evolutionary algorithms use the operators we can see in the evolution of the living beings, or some animals, or some in animals in general. So swarm intelligence use the system or the way or the behavior of animals in a group. So I'm gonna show you more details. It's a set of nature-inspired computational methodologies and approaches to address complex real-world problems to which some math or traditional modeling can be useless. So this is one of the characteristics of computational intelligence. We don't worry too much about math. We don't try to modulate or what is the rule or the theory in math that the algorithm use. Actually, there is a recent open research. Some people is trying to set some rules or math inside the algorithm. But the origin is, okay, we don't worry about it. Why? The process might be too complex for mathematical reasoning. We can think about three dimensions optimization problem or 5 dimensions. But what happens when we have 100 dimensions or 1,000 dimensions? It's really difficult to deal or to handle with that kind of problem. But these algorithms have been demonstrated that deal with this situation very well. It might contain some uncertainty during the process. That is, we don't know what is happening. There is like a black box. And the process might simply be stochastic in nature. So that means every time the probability about one event is different, right? So specific with evolutionary algorithms is a population-based meteoristic optimization algorithms. Use some mechanism inspired by biological evolution as reproduction, mutation, recombination, selection, There are many papers showing some another operators. One solution is a candidate. Play the role of individual in a population, and the fitness function determines the quality of the solution. So we can imagine, for example, we are trying to find the best way to sit, for example. And we don't know if the best way to sit is like this or like this, you know, what is the best way? But we want algorithms to find the way. So every of you is it in a specific way. So one of you is a solution, right? So if we use a ways how somebody see it and we can combine, so maybe we can find the best solution. But who or what we're gonna evaluate what is the best solution? So this is one of the most important part in our evolutionary algorithms, our objective function, our fitness function. So evolution of the population then takes place after the repeated application of that operators. So you can imagine a knapsack problem. This is very basic problem. So we have a knapsack or a backpack, and we have some items. Every item has a value and a weight. So we have a constraint. In that case, it's 15 kilos, right? So what is the best combination of items in order to maximize the quantity of value considering our constraint? Our constraint in this case is 15. So we can see, for example, if we take this one, so we almost fill the backpack is because it's 12, but we have only $4. And we can use this one or this one. No. If we select these two, so we have 13 kilos and only $5. So we have some constraints, Z, W, and that satisfy this situation. We have an objective function, Z of X, a vector X that satisfies the constraint W. And if we have a maximum result, then X is optimal. So we have these easy constraints, right? So we can modulate that problem with that table. So every item, you can imagine, it's a different, right? We have 10 items with different values and different weight. So our constraint is 100. So what happens if we use binary codifications? So we say the first item is considering. We take the first item because it's 1, and the fourth, 8, and 9. So in that case, we have a value of 306. And this is a good value? Yes, because we are satisfying the weight. In that case, is 72. Is less or equal than 100, right? So this is one of our solution, our candidate. This is an individual inside the population. The population can be, I don't know, 5 or 10. So this is a good solution, right? So considering this solution, we are taking now number 2. So the value is 726. So we increase the value just adding one item. And the weight is 87. So we are satisfying the constraint, right? So it's a good solution. But what happened in this case? We take the item number 10. The value is 731. Is better than the previous one? Yes. But our backpack gonna fall or gonna break, right? So it's not a solution. So our possible combinations here is 1024, 2 to n. This is a very basic problem. Again, what happens if we have 100 dimension, 1000 dimension? It's really difficult to deal with that problem. So we have some operators. you can imagine every individual as a possible solution, and we can combine, we can select, combine, mutate every solution. For example, we have these two solutions, and we split the solutions. We have A1, A2, B1, B2, and we can create a new individual. So we have the individual A1, B2. Considering A1, considering this part and this part. So we have this solution is a good solution because it's respecting the constraint, satisfying the constraint. And we have the second one, right? But it's worse and it's worse. So our solution, our good solution is the first one. Okay? So in general, we initialize randomly or with a specific strategy our solutions. We make a selection, and we see if we satisfy our some stop condition. So we got a good value, at least, for example, I don't know, a good value. So we have 1,000 iterations, 10,000 iterations, or along some iteration there is no any changes. So we can make a crossover mutation. So at the end, we have a search space we don't know, and the solutions are moving in the search space, looking for some good value, right? So we can say evolutionary computation has some of neural computation and part of natural computation and machine learning. So this is a set we can see. Okay, and the last one, swarm intelligence, is a machine learning technique inspired by the collective behavior of decentralized, self-organized systems. Is used for solving complex problems through agents that follow simple rules and interact with their environment and the other agents. The strength of swarm intelligence is his ability to solve problems collectively and adapt to changing environments. So this is a pseudocode. It's very close or very similar to evolutionary algorithms. We have a group of particles and evaluate the p-best. We can see if the current position is better than p-best. Along some iteration, we are looking for the best value. What is the difference? In evolutionary computations, we apply operators. So our individual can change, can or not, right? But in swarm intelligence, one of the most popular algorithms in swarm intelligence is PSO, particle swarm optimization. By the way, there are many algorithms inspired in the behavior of animals. For example, wolf, whales, ants, bees. There are some others, I don't remember the others, but why? Because the behavior of animals in groups has some intelligence and is worth to try to apply in these algorithms. So these algorithms are inspired in that behaviors. So we can see a search of space, and we are trying to find the star, for example, and we initialize the particles randomly. We don't know where is the star, but at the end of many iterations, the particles are good to find where is the star. Actually, I'm going to show you next Thursday one implementation, and we're going to see the particles moving around the search space. So we have a p-best, and g-best is has a relation with the other particles in the search space and trying to move the particles to different places. You can see, for example, birds. You remember how birds in a particle swarm are moving. There is not a linear direction, but the birds move to a place and enlarge and shrink, because this behavior is a good way to do optimization. And so we can see some function. So what is the global minimum? Is difficult, but here is a little bit more complex because we can initialize the particle in this place. So what is the best place to move? This part or this part? You notice that it's not 2D, right? Or 1D is only one way. No, we have a 3D here. So what is the best way to find that global minimum or maximum? So that is a different way to see, and we can see, for example, I'm going to show you in the next Thursday, in this Thursday, the implementation of these three benchmark. The very basic function, a sphere, rastringing. Okay, we can see rastringing and Rosenbrock. So how the algorithms goes to the global minimum or to the global maximum depends about the approach. So we can see the functions for every the mathematical explanation for every function, and we're gonna see how the algorithms, the particles move along the surface space and at the end converge to the global minimum. Okay, so time for demos, gonna be in 2 days, and let me know if you have some questions.
Any quick questions for Luis? Probably have a lot.
So in the presentation, there are some links you can use to read more. Okay, thank you.
Yeah, Luis covered a lot of topics. See you on